Hello. Hello everyone. My name is Ashwin G. Kumar. I have completed MA English and currently I am pursuing Master's Certificate Program in Artificial Intelligence at Sri Shankaracharya Computer Center and Pragyan AI and ES School. Today I am going to discuss about Advanced Machine Learning Time Series Model Case Study. Here, this is my topic: Bitcoin prices based on historical trends. This is a data set. I am using. Here, first of all, we discuss about what is time series. A time series is a sequence of data points collected or recorded at successive time intervals. It is used to analyze trends, patterns, and dependencies over time. Time series data is commonly found in various fields, including finance, economics, weather forecasting, stock market analysis, and machine learning applications. These are the key characteristics of time series data. The first one, time dependency. Second one, trends. Third one, seasonality. Fourth one, cyclic patterns. Fifth and last one, stationarity. It's a topic, Bitcoin prices based on historical trends. Here we discuss about the data set. The BTC/USD trading data set from Kaggle contains historical Bitcoin prices data against the US dollar, capturing key attributes such as open, high, low, close, volume, and market cap at daily intervals. The dataset is essential for time series forecasting as it provides insight into Bitcoin's price trends, volatility, and market activity. The cross price is often used as the target variable for prediction, while features like high and low prices help capture fluctuations. The volume and market cap provide additional context on trading activity and overall market value before analysis. The pre-processing steps include handling missing values, converting the data column to datetime index, and resampling if needed. This dataset is valuable for developing predictive models like ARIMA, LSTM, and SARIMA to forecast Bitcoin's prices and assist in investment decisions. This is a column included in this dataset. First one, date, open, high, low, close, volume, market caps. First of all, we import the ARIMA model. Sorry, install the ARIMA model, and then we import libraries using pandas, numpy, and other basic things. And then we load the dataset using this function. This is the dataset URL. It is daily.csv. And then we print the first 5 rows of the dataset using this header function. And if I check the information of this dataset using this info function, and then we find the missing values using this function. After finding these missing values, we can understand that here there is no missing values exist. And then we convert the date to datetime format using these functions. Here, this code df of date equal to pd dot to underscore datetime of df of date converts the date columns to datetime format, enabling time-based operations like sorting and resampling. Using df.headof verifies the change. If error occurs, the error equal to coerce can handle invalid dates by converting them to null. The setting date as the index of df.set underscore index of date, comma, in bracket true is useful for efficient time series analysis. Maybe check the information here. The date changed to date format. And then next step, that is EDA. Here we visualizing the Bitcoin prices using this plot. Here this plot, the historical deflation prices to understand the trends in this data set. Here, this given matplotlib code generates a time series plot of Bitcoin's closing price over time. It first sets the figure size of to 12 into 6 inches for better visualization. The plot of function then plots the closing price df of close in blue labeling. It has a Bitcoin close price. The x-axis is labeled as date, while the y-axis represented the price in USD. A title, Bitcoin price over time, is added to provide a context, and a length legend is included to identify the plotted line. Finally, the PLT dot the plot making the show off displays the plot, making it useful for analyzing trends and patterns in Bitcoin prices over time. And then we check the trend detection using this ADF test. This is a function here. This given function performs the augmented Dickey-Fuller test ADF to check whether the Bitcoin's closing price data is stationary. It takes a time series as its input and applies the add Fuller-Off function from the stat model library. The function prints the ADF statistic, which indicates the strength of stationarity, and the p-value, which determines statistical significance. If the p-value is less than 0.05, the data is stationary, meaning it does not have a significant trend or seasonality. Otherwise, the data is non-stationary, indicating the presence of trends or seasonality. This test is essential for time series forecasting, as most models requires stationary data for accurate predictions. Here, the data is not stationary because it is not less than 0.05. And then we use the first order differencing using these codes. This code applies first order differencing to the Bitcoin closing price data using df of close underscore diff equal to df of close dot diff of, which removes trends and helps make the data stationary for time series modeling. Since differencing introduces a NaN values in the first row, diff dot dropna of in plus equal to true removes it to keep the dataset clean. This process is essential for ARIMA models and other time series forecasting techniques, ensuring better accuracy. By stabilizing the data after differencing, it is recommended to rerun the ADF test to confirm stationary. And then we check the stationarity using ADF again. After using this function, we can get the data is stationary because here the value is less than 0.05. And then we find the best ARIMA model parameter using these functions. And then we train the ARIMA model. Here, the ARIMA model is widely used time series forecasting method that captures patterns in historical data to make future predictions. It is effective for datasets with trends and seasonality. This is ARIMA model. Here we train the ARIMA model and print the model.summary. So output we get. And we displays the plot Bitcoin prices of forecasting using ARIMA function. ARIMA. And then we split the data into training and testing using these functions. And then we evaluate the model using the MAE and RMSE scores. This is the output we get. And then next step, we using the min-max scaler. Here, this code normalizes the Bitcoin closing price data using min-max scaling. which transforms value into a range between 0 and 1. The first DF of Rebecca Coase values extracts the closing price as a number array, then min-max scalar of future underscore range equal to 0, 1 is applied to scale the data, ensuring that all values are within the specified range. Finally, scale.fitof function fit underscore transform of data performs the transformation. This normalization helps improve model performance, especially for neural network and machine learning models by preventing large value differences from dominating predictions. Here we create a sequence for LSTM, and then we split the train test using these functions. This is a train size and test size. And then we build the LSTM model. The LSTM model, that is long short-term memory network, is a type of recurrent neural network RNN designed to process and predict sequential data such as time series, speech, and text. Unlike traditional RNNs, LSTMs can remember long-term dependencies, making them ideal for tasks like Bitcoin price prediction, stock forecasting, and natural language processing, that is NLP. So the LSTM model we built. We compare the model and print the summary. We're using the optimizer Adam to compile the model. This output we get here. This code builds an LSTM model for Bitcoin prices prediction using a sequential architecture. It consists of three LSTM layers with 50 units. 50 units. Three LSTM models with 50 units. Each were the first two return sequence to allow stacked LSTM processing. The dropout layers of 0.2 are added to prevent overfitting. The final dense layer outputs a single value predicting the next day's price. The model is combined using the Adam optimizer and means code error, this MSC loss function, ensuring efficient training. Finally, the model summary of provides an overview of the model's layers and parameters. We will train the LSTM model. This is output we get. And then we plot the training and validation loss using this plot. Here the x value is epochs and y value is loss. Here, this code plots the training and validation loss over epochs to analyze the LSTM model performance. The plot.plotoff function visualizes the training loss of blue and validation loss of red. Using data from history of loss and history of history of val underscore loss. The x-axis represented epochs and the y-axis represented loss means scored error. This plot helps identify overfitting or underfitting, ensures the model generalizes well to unseen data. And then we make the prediction, the LSTM model. Yeah, this code makes prediction using the trained LSTM model on the test dataset of X test. The predicted value y are in the scaled format. So scalar.inverse underscore transform is applied to both actual y-test actual and predicted y-pred actual. Y-test actual and y-pred actual values to convert them back to their original price range. This step ensures that the results are interpretable in terms of real Bitcoin prices, allowing for proper evaluation of the model's performances. The model evaluation we using MAE score and RMS score, which is a scores output we get. Then we compare the model performances using this one function, both ARIMA and LSTM, which is a scores we get ARIMA model and LSTM models. Here, after comparing these model performances, the best model is ARIMA because the ARIMA has the lowest MAE and RMSE, meaning it provides better accuracy than LSTM. And then the LSTM has higher errors, indicating it might need more tunings. Based on the evaluation matrices, the ARIMA model outperforms the LSTM model in predicting Bitcoin prices. The ARIMA model achieves a lower mean absolute error, that is MAE, of 90.80 compares for LSTM, indicating that ARIMA's predictions are closer to the actual values on average. Similarly, the root mean score error (RMSE) for ARIMA is, which is also lower than the RMSE for LSTM, suggesting that ARIMA has smaller overall prediction errors. These results indicating that ARIMA provides better accuracy and reliability in forecasting Bitcoin prices in this case study. Thank you.